Hey folks, I'm Vanija, and I'm going to be giving a talk on the AI agent landscape today. We're going to be covering several topics, right from agent patterns, the foundations of how they're built, how they interact with each other, to evaluation, to leaderboard, all the way up to current research within the space that I'm really excited about. And a bit of background on me. I currently work at Google. I work on multimodal agents, making them as robust as possible. I work on a lot of evals and a lot of training as well as post-training parts of Gemini in order to make that happen, to have Gemini live on our downstream products. Prior to that, I was at Meta and I was working on the personalization recommendation space, kind of integrated with generative AI. Really excited to be here. I've collaborated with Dr. Das for quite some time, so really excited that we can make this happen. And sorry I couldn't be there in person, but would love to take any questions after the talk, whether offline on LinkedIn or through Dr. Das himself. And with that, let's get started. All right. Let's start with the sharing. Yep. On screen, desktop, share. Two. Sorry about that. Yes. And yes, perfect, finally. Okay, now let's get started with the slideshow. All right. So like I mentioned today, we'll be covering quite a lot of broad topics within the AI agentic landscape here. And a quick intro on what our talk will look like here. We'll start with, how do you even kind of define an agent? What are agents? We'll cover real world problems that agents look to solve, design patterns, key agents that you could be using in your day-to-day life, leaderboards, and some exciting research. Let's get started. All right. So kind of what we can do here is as we talk about the real world problems agents aim to solve, we can kind of also reverse engineer and talk about what the agents actually are and what they are fundamentally. And we'll cover a lot of that with the design patterns as well to be able to kind of understand internally what is an agent, right? So let's back up a bit and let's talk about real world problems that agents are aiming to solve. The biggest area where we're seeing agents kind of come in now is customer support and virtual assistants. You could think of any customer support, like say perhaps you're calling your phone company for a problem or your utility company. You could be on hold for quite a long time because these companies, receive quite a high volume of repetitive customer queries, for refunds, tracking, account issues. The AI solution is quite organic to be plugged into here. AI agents, these could be conversational agents, these could be chat agents, or voice agents, which are basically looking to handle natural language, retrieve information, and escalate the complex issues. The benefit here is that they can run 24/7, they have lower operational costs, and then faster response times. And a lot of times when they say there's a specific industry that's requiring custom logic or custom flows for what their representatives need to know to be able to assist customers, there's a lot of things that we can do to alleviate that pain by, say, adding in a retrieval augmented generation pipeline where you infuse a lot of the knowledge base for that company within the vectors database and then retrieve it real time to be able to maybe chat with the person to assist them the best you can. So that's for the customer support use case, and we're actually kind of already seeing it live. We're seeing it deployed across several companies, and we're seeing it both in terms of agentic flows as well as just simple workflows. And to give a quick difference here is agent flows run more autonomously, whereas workflows are very structured and defined, and there's no variability and there's no sort of thinking or processing that the agent has to do by itself. For example, say your customer support flow, just requires the person to come in, and when they ask for an account issue, there's an API call that you trigger once you fill in the parameters with the metadata of that customer, their account information, their name, their location, anything else that's relevant to that. That would be a simple workflow because the only kind of open-endedness here was the understanding of the user's query and then mapping it to the right output task. On the other hand, an agent flow itself, what it would look like is having more open-endedness, maybe having more gray areas between two queries, maybe, account issues, and then could have maybe multiple different outputs, not just an API call. Maybe it would also involve having a financial advisor within the company take a look and have the person kind of issue their back payments, or it just requires something a little bit more than a simple crafted out endpoint. And that's kind of where the agent flow would kick in. So other areas where you can deploy real world problems for where you can kind of deploy agents to solve real world problems is healthcare and medical automation. In healthcare, you have overloaded clinicians, diagnostic complexities, admin inefficiencies. There's so many places where AI can be sort of deployed within the healthcare space. You can monitor patient vitals, you can detect anomalies, you can assist in diagnosis. You can automate a lot of the admin tasks, scheduling, following up with patients, sending claims to insurance, for example. Um, can help kind of speed up the process quite a lot. On the other end, it can also help within the research side in drug discovery, and kind of help alleviate and take off a lot of the menial tasks from the human, to be able to give them a lot more autonomy and freedom there. The other space that we're seeing them creep up more is the finance and fraud detection. So there's, rapid fraud patterns, high-speed trading, risk assessments, and these are very critical and unable to be solved by traditional software systems because the patterns can be quite variable there. So with an AI solution, what you can do is have agents detect these anomalies in transactions, analyze, the different markets and recommend the trades. Um, so what you'll have is you'll have the benefit of reduced fraud losses, faster analysis, and improvement of the compliance. This can be done a lot faster. Anomalies for different folks could look like different things. And that's where you would really need the agents to kind of come in and understand those patterns, those spending, those buying patterns for each individual to understand whether there's a fraud taking place or not. Now let's go on and talk about the design patterns. Now, there's several design patterns that you'll kind of see when you're looking at agent frameworks. I've picked these four as I see them kind of as the most relevant currently, but there's definitely several more that are coming in that may be more tailored towards your use case. These, however, are very key and very critical, at least at the kind of ground level, at the base level to start off with. The first one is reflection. Reflection is likely one of the most key pieces to having your agent system work as efficiently as it can. And basically what reflection looks to do is it's looking to improve the performance by kind of critiquing their own output, right? So what you'll have is you'll have an iteration of what you've asked the agent to do. They'll produce the output, but instead of just taking and gearing the output out to the user, what they'll do is they'll reflect on what the output is, refine it, and then get it back to the user, kind of similar to how humans work in that case. So LLMs will be improving performance by critiquing their own output. Um, the workflow would be basically, like I mentioned, generate the output, critique it, revise it, repeat it. And like I mentioned, it mimics the human feedback loop for iterative improvement and iterative improvement on the model itself. This can help different kinds of issues in code, in writing, in reasoning, summarizing, conversational, and basically it works alone. So you can either have self-reflection or it can work with a critique agent, and it can have a separate agent that's unbiased and looking at the output of the agent to be able to determine whether there's a need for improvement, if there's any bias, or if there's anything that can be kind of corrected through the process. You can enhance this further, definitely with tool feedback. If it's code-based, you can have unit tests, you can have web searches. It can be pretty lightweight to implement, but it can kind of yield significant quality gains. I do want to add the caveat here that the lightweight to implement really depends on how you decide to sort of implement this. If you're looking at having a panel of critic agents, or something a little bit more robust, the lightweight nature of that definitely reduces significantly. And going over the quick example here by Andrew Ng, he starts by asking a question, just please write a code for this task. The coder agent takes that task and starts writing the different functions. Then you have a separate critic agent here who's looking at the code that's been generated by this coder agent and finding out that, oh, there's a bug on line 5. Let's fix it by doing XYZ. Oh, it looks like it failed unit test 3. Let's try changing, this specific thing within that function. A lot of this is kind of how humans work together in an environment. And the more you kind of work with agents, the more you'll see what they're doing is they're basically mimicking the entire environment of how humans are working together. So this is an example of how PR reviews work when you push or commit your code and you have your peers review it. They'll give you feedback. Even before they give you feedback, you'll get feedback from your unit tests when they're failing, any integration tests, anything else that's going off. So that's kind of mimicking that environment. And the benefit of this is as it outputs, you will be getting the best coding result that you could because there's already been so much revision happening in the background that you haven't seen. So the example here was, here's the code intended for task X, with the previously generated code. Let's check the code carefully for correctness, style, and efficiency, and give constructive criticism for how to improve it. And this could be example of a system prompt that you kind of give the critic agents. Of course, you would likely have it even more detailed, maybe with a few shot examples of how to review the code, where to specifically look. Maybe, it will also do tool calling and call in different tools to be able to kind of compile and understand the code, especially if there's a lot of integration within the system. So, this would definitely be very helpful in kind of producing the best output that you can get. So this is reflection. And next, what we'll do is we'll look at a few papers where they implement variants of reflection. So the first paper is Critic, and this is done by Microsoft Research and Microsoft AI, in collaboration with Tsinghua University as well. And you can see their overall architecture. They have this sort of two-step process of how they're doing reflection. First, what they're doing is they come with it in the input. They go into the black box LLM. It produces the output. they then verify, and this is where I was coming to, where you can do verification that is tool-based. So maybe your task requires calculation. You can call a calculator. You can search Wikipedia for facts. You can search a knowledge base. Maybe it's your own vectors database or a different knowledge base that you have. You can look at a code interpreter, text APIs, search engines, what have you, to be able to verify your output there. Once you're able to verify it, you can start critiquing it, right? So you can start basically correcting the output based on the feedback that you've received from the critique. And then in this iteration, you'll basically be able to correct your initial output and then give it back to the user. So this is one framework that we've seen, and it's worked well, and it's quite a simple framework to implement as well. The next, what we'll see here is called self-refine, and this is iterative refinement with the self-feedback. This is with Allen AI, Allen Institute for Artificial Intelligence, NVIDIA, Google Brain before it was called Google Brain. Now it's DeepMind. So quite a mix of collaborations here. And what they're doing is they kind of have this three-step here where you kind of give the input. It looks at self-refining by starting the generation of the output and then passing it back to the same model actually. That's the difference here compared to the prior paper. Then the feedback, once it's passed back to the model itself, it refines on its previously generated outputs, and that's going to be step two. And then it'll basically be iterating on the loop. It'll keep refining, it'll keep generating the feedback, it'll keep refining, generating the feedback until you hit the terminal condition, at which point it will generate the output. The key thing to note here is that they're looking at leveraging the same model itself. There's obviously different design patterns you can do. You can have different models here sitting and doing different tasks as well. So this was what self-refine kind of gave us with the iterative refinement with self-feedback. Now looking at the next pattern, this is tool use, and this is likely one of the most common patterns that you can kind of come across when you think of agentic structures, right? Tool calling. It's been very, very beneficial. So it makes sense why it's been so popular. So tool use basically allows the LLM to call external functions to gather all of the information. Then it can take the action or it can manipulate the data. And by doing so, it extends beyond its own capabilities. So, we've seen examples already of tool calling, but to kind of solidify that a bit more, you can have web search tools, you can have code execution tools, you can have even simpler tools. You can have weather lookup. You can have flight lookup. You can have API calls that are doing a lot of things that are very custom for your system to be able to kind of look up and understand. So say you have a specific user come in and they're looking to understand some feedback or something within their account. You can have API calls that are called externally to give information and augment the current information that the agent has to be able to respond back to the user. And extended tools that you can use in agentic flows could be there for, various reasons. Could be there for searching various sources too, like what we have web. You can do a search on Google. You can do Wikipedia. You can even look up archive papers, and other databases as well. You can have productivity tools. You can have email handling, calendar management, file access, and many other integrations too. And you can have a lot of generation of image or video tools, that are going to be generating or kind of interpreting images. So you can have object recognition, image generation, video generation, and those can be tool calls as well. So a quick example here from the batch by Andrew Ng was in this design pattern for tool use, you can kind of have, the web search tool where you go into Bing Copilot and you ask, what is the best coffee maker according to reviewers? Now, in order to best answer this, what you'll need to do is a web search. So it'll be searching for the best coffee maker according to different reviewers, and then it'll be analyzing that information, summarizing it, and getting it back to the user. A different example from ChatGPT on code execution is and then an investment question. So if I invest $100 at compound 7% interest for 12 years, what do I have at the end? So it's going to break down your problem. It's maybe going to call a calculator, or if your question here was even more complex, maybe it was based on taxes, and taxes work differently in different states here. So then it would need to do a search for your state to understand your situation, get those numbers, and then be able to call the calculator to be able to do the calculations for that, and then have it geared back to you. So these are some examples of how tool calling can work. You can obviously, like I just mentioned, you can have multiple tool calling nested within each other. You can just have single tool calling available. And it's basically the planner agent's job to understand which tool it needs to call based on the query it's receiving. So the general structure of how agents work is there's centrally a planner. And this is just an LLM, and it could be fine-tuned, or more recently, I've seen, because the LLMs are getting better and better, you could just have it fed into the system prompt on the tools and the capabilities that it has available to itself, and give it a few scenarios of when to call each tool. For example, if the user is asking for any mathematical reasoning capabilities, maybe you want to call the calculator. If they're asking for, say, reviews for a coffee maker, you want to do a global search. Give it those few examples, and then what it's going to do is it's going to take the user's query as input, and it's going to output the tool call. Whether it be, generating an API call, whether it be calling maybe at different databases or what have you. So that's what the planner agent's going to do. And that's basically what lives at the center of the agentic architecture framework. The rest of it is very custom, very use case dependent. The number of tools you choose, how you choose to do a reflection, where you keep your memory or knowledge base for the agent, whether you need the memory or knowledge base for the agent, whether you want to cache results that are often kind of asked. So maybe if, say, your agent for some reason is weather related, and it's used heavily in a specific region in say California, then maybe you want to cache results for the weather for that region, because it's going to be queried quite a lot for the users. So this is just an example, but caching is also something that you can kind of add into your overall design pattern. But so this is how we can use tool use. There's also, by the way, several interesting papers on different ways that you can do tool use. They're already linked and listed in my blog, Venetia.ai, under agents. So feel free to take a look at that. For the sake of time, I think we'll move on to the next design pattern here, which is planning. So this is kind of what I had briefly started talking about already. So planning is the agentic AI design pattern in which the LLMs kind of autonomously decide the sequence of steps required to complete a task. Planner agent is quite critical for any agentic system, because its kind of purpose is to enable the agent to break down high-level goals into smaller, manageable tasks, right? Like researching subtopics, synthesizing information, writing reports, breaking down a big coding task into small little subtasks to be able to iterate on it and then refine on it. So here's an example of a planning agent in action. So say during a live demo, an AI research agent faced a web search API rate limit error. The agent autonomously switched to a Wikipedia search tool and completed the task successfully. So this behavior kind of demonstrates the true autonomy and adaptability and kind of the AI agentic moment. This is again going back to our first slide where we talked about the difference between agent flows and workflows. This is clearly an example of an agent flow where it ran into a blocker, realized it still needed to be able to find a solution, figured out a workaround, and got the answer still back to the user. Now, in a workflow traditional system, what you would have is the agent would be told that, you have to call this API to be able to get that answer. There's no room for creativity or adaptability, and you would have hit that error. And then you would have to just go back to the user with that error. So that's kind of the difference where in the agent workflow, you're able to think more autonomously, come up with creative solutions, and come up with a plan given any scenario that you're kind of in. It's a structured planning output. The LLM plan specifies multi-tool calls in a sequence, and it triggers software to kind of invoke the tools step by step to complete a task. So downstream, the tools could just be a software system that are running. The main point is to be able to get all of that information back to the agent so it can kind of comprehend it, massage it, and get the results back to the end user. So this is planning. Now we'll move on to kind of multi-agent collaboration. And this is a very real scenario. So what we've been talking about right now is individual agents, but this is a scenario with multi-agent collaboration. And again, to be able to kind of understand it better, you can think of a real life scenario where you have humans working here instead of agents. So say you are a tech company and say you have a designing team, right? So the designing team is the C-suite team here. It's the CEO, CTO, CPO. Then you have your coding team. This includes the CTO, programmers, designers, and then you have your testing team, which is just going to do a lot of reviewing. Maybe they'll do some programming, some testing, and then a documentation team. You have your CTO, CEO, CPO programmers here. Now, this is the traditional, waterfall model where you'll have each human designated to a specific task. Each human is specialized for that specific task, and that's why they're kind of tapped on their shoulder to kind of perform this, and it works. So the reason it's waterfall is because it runs sequentially. There's no general room for parallelization here. And this is the example where it is running with humans, right? Humans are not great in this collaborative environment to kind of take these key pieces and move them around and start kind of, maybe documenting a piece of code that just got tested, even though, say, the entire class or the entire, the problem statement wasn't fully implemented, at least starting to iterate on it and chip away at it bit by bit. On the other hand, what you can have here is a chat chain system here, right? Where the CEO is the instructor in this case, and you come in with a task and you have your assistant, the CPO, you kind of put in the modalities that are needed, and then you put in the language that is needed, and then you start coding and you start iterating on the coding. And the different iterations of the coding run through the designer, the reviewer, the tester, the programmer, the CPO again. And then it can kind of come back to manual. Now, this is one example. Different examples could be where you have agents, that are highly specialized in a specific thing. So maybe, you can think of drug discovery. Maybe there's an agent that is very specialized in a specific chemical or a specific drug, and we're looking at researching a problem. So then our current, like our entry point agent system, gets this question where they're stuck on the drug development procedure, and then they tap on the drug development agent, which can have several tool calls of its own. It can have several databases of its own, and it can understand the granularities that the prior agent wasn't specialized enough to do. Maybe this agent has been fine-tuned on more drug-specific data on the kind of the science behind it. So this is kind of a different example of how you can think about it. You can have this entire ecosystem of different agents working together and just kind of communicating within each other for specific specialties that are needed from each individual um, kind of structure itself, if that makes sense. You can also kind of think of it in a coding environment where you can have, like somewhat similar to here, where you can have agents that are very specialized with working on the QA, working on the testing portion of it, um, versus agents that are, there to just document the code and have it out to the agent. Or you can kind of have all of that compressed into one system itself. That's kind of the uniqueness of this, where there's no right and there's no wrong to how you develop your structure. It's very dependent on use case. And in reality, what happens is the constraints come in forms of cost, budget, as well as latency, um, and complexity in terms of implementation. What you'll have with multiple agents calling each other is definitely quite a lot of complexity, a large amount of cost, to keep all the systems running, to keep all of the databases maintained there. And also just even in terms of maintainability, if there's a failure in the system, it gets so much more complex when you start adding even more elements to it. So those are just some things to think about as you start crafting an agent system yourself. All right. Now I wanted to cover some key agents that, you may be using in your day-to-day that you may not have given too much thought of. So ChatGPT being the first and foremost, where it's a conversational agent that first it takes in your text, interprets what you're saying and reasons on it, and then generates an output. And the output can basically involve searching the web. It can involve searching archive for paper-specific questions, for research-specific questions. It can do a lot of different internal tool calling itself. If you ask it for a code sample, it can, run its compiler to make sure that the code is executable before sending it back to you. So in that sense, ChatGPT is an amazing agent in and of itself. Claude similarly, does a lot of contextual reasoning. It can read documents, it can summarize, plan multi-step tasks. Gemini, on the other hand, being multimodal, it can perceive text, images, videos, and kind of provide an integrated response to that. So all of those are kind of in the same, similar category of a bucket of agents there. Then you have Copilot, you can have Microsoft Copilot, GitHub Copilot, there for coding productivity agents that are looking to observe the context and suggest and complete code or documents. You have Perplexity, that's kind of working more as a research agent, kind of helping automate a lot of your search, retrievals, and kind of evaluate and summarize the web information autonomously. You have Replit, you have Cursor. Cursor is great in terms of coding. It learns the project context and proactively generates and modifies the code. So basically what Cursor is, it's an IDE in itself, and as you import your repo, it's able to analyze your entire code. It's able to help you fix bugs, fix, either small issues, create new features, all with just a simple kind of text or a prompt. The more descriptive you are, the better outputs you can get. And all of this is not, done without permission. So for every step of the way, Cursor will ask for your permission to modify your code, and you can accept the changes. You can choose to accept them, reject them once you've tested it out, and choose to kind of update your repository with those changes or not. But it's very cool to see that you can have a entirely very large code base. Maybe it could be AI, or it could just be pure software, backend, front end code, but it's able to fully take that code base within its context, understand the relationships between each of the different files and components, and not only kind of help fix any issues in it, but also kind of augment um, what you already have, which is quite impressive. I think for a human to take on that task could be quite tiresome and could involve a longer latency. So it's kind of nice to see how these can help improve productivity. All right, next what I wanted to do is talk a bit more about leaderboards. So there's quite a few leaderboards that are emerging now within the agent space, and it's really exciting to see. This one is Galileo Agent, and this is the V2 version of the leaderboard. It is domain specific, so you can have healthcare. There's several other domains too, and you can kind of it's interactive. It's on Hugging Face. You can tune out the different parameters that you're looking for within your search. And what it will basically help with, for example, here I just took a screenshot of the healthcare use case. You can see, which model works best for, in this case, it's Mistral Small works great for open source when the output type is normal. Vendor is obviously Mistral here. The average action completion here, and this leaderboard basically is specifically measuring tool calling and multi-tool calling interaction decision making across the different business scenario data sets. So you'll see the average tool selection quality here also given as a metric, which is very critical. The cost, like I mentioned earlier, is also one of the constraints in terms of designing. Average duration and average turns, basically how many turns did it take to complete your tasks. So you ideally would want minimal turns and best output. But so here we're seeing Mistral scoring in at first, DeepSeek V3 coming in at second, and third is Color by ours here. So this would highly recommend taking a look at it and playing around with it for especially for other domains. It may surprise you what models appear here in terms of, ranking kind of at top 10. So yeah, feel free to take a look at this on Hugging Face. There are quite a few as well. Other leaderboards that I'd highly recommend to take a look at. So there's the Holistic Agent Leaderboard, HAL, and this is by Princeton University. And what it is, it's basically a third-party evaluation for agents. It's again, this is also cost aware across multiple benchmarks. So you have the coding, the web navigations, the customer service benchmark. So this is pretty neat. I definitely recommend taking a look at this. You also, SWE-bench has been there for quite a bit. You have the SWE-bench leaderboard, it's a benchmark and leaderboard focusing on software engineering and coding agents. So, solving coding tasks, integrating with development workflows. Then you have the ASTA bench by Allen Institute for AI. And this benchmark is basically this benchmark and leaderboard for AI agents is there for scientific research tasks. So more think of open-ended tasks, um, machine learning research, things that are kind of maybe something that ChatGPT wouldn't be able to give you a quick answer for. So that's kind of where AstaBench comes into play. And then excuse me, you have the Open Agent Leaderboard. So this is an open source framework. It's based off of Agent for kind of assessing agents across data sets. So you can have, math, reasoning, and it will basically rank all of their performances. So wanted to highlight this in terms of looking at different kind of leaderboards to be able to help understand which models to choose for which parts of your architecture there. And now, wanted to delve kind of into two quick papers that I've come across recently within the agent space that I thought were pretty cool and wanted to share. Would recommend that you take a look at these after this, but here's a quick synopsis. So this is Robust Agents Learn Causal World Models, and this was published in iClear in 2024. This is by DeepMind. So what this paper looks to do, it's exploring how agents can or how they can generalize under the distributional shift by learning internal causal world models rather than only associative patterns. This paper is basically looking at asking, do agents need to acquire causal models? For example, a model of how the world works, or and kind of getting beyond the mere correlation of how the world works, for instance, uh, and kind of getting that in order to be able to be more robust and more generalizable, and why it matters. So basic kind of core and crust of what they were getting at here is many agent architectures today rely heavily on LLMs, or kind of behavioral models trained on huge data, but they lack the causal understanding, and they may fail when the conditions change in new or novel settings as they're coming across within their interactions. So this paper kind of pushes the envelope in making the agents more human-like in terms of reasoning. So, but in more of a causal sense. So, you can think of like if I press this button, I get this output. If I do X task, I get Y output. So kind of going into a more causal reasoning mindset to be able to function and understand new and novel scenarios that may not have been part of their training, and in that sense working more like humans. And the key kind of takeaways from this paper that I thought were relevant here were for agents to kind of act robustly. What the paper says is they kind of have to move beyond reacting to inputs and more towards modeling the world and planning kind of through that model of the world that they've created, and adapting when things shift. And that's kind of where the causal reasoning comes into play, because in order to create that model of the world that they need to have to be able to understand how to work in these novel scenarios, they need to understand the causal relationships that happen in the world. So they need to go beyond just the simple data that they have. They need to understand that within this environment and the world we've created, if we do X, then Y is expected to happen, so that they can kind of take that and stretch it into reasoning. That, when I come across a new scenario based on my experience of this world model, I should expect, XYZ to happen. That's kind of what they were going towards with robust agents here, learn causal world models. Um, and now the next one here. This was another paper that I thought was, pretty interesting. I would also recommend taking a quick read at this. And this paper is by Meta Fair Labs, which is now part of Meta Superintelligence. And what it is it's collaborative reasoners, self-improving social agents with synthetic conversations. I thought this was pretty interesting and a very unique topic, specifically. So what this, if I remember correctly, what this paper did is it introduced this framework, and it called it Coral. So you'll see it here, and it calls it collaborative reasoner, or Coral framework, that it proposed within this system. And what it does is it builds social agents capable of improving themselves via synthetic conversations that they have among the agents itself. And these agents aren't just kind of single user chatbots, but rather they're kind of more an ensemble, or a peer that interacts, reasons together, critiques each other, and refines the outputs. The kind of essential pieces and components to agentic social reasoning. And I thought it was kind of cool that they pulled in a lot of the topics that we covered earlier in the talk as well, about the reasoning together, critiquing, refining the outputs, and reflecting. So, basic general core and gist of this paper, why it really matters. The real world agents kind of often interact with humans and other agents, being able to self-improve, collaborate, even debate internally or in a multi-agent scenario, which is a kind of a if you think about it, a really powerful step towards making very flexible and making very robust agent systems itself. And the key takeaway from this paper was the agent architectures are kind of moving from, you know, one agent gets this input and then it needs to produce this output towards more of an agent cells interacts, refine, learn. They do this through either themselves, self-reflection, or through an ensemble of other agents where they can reflect, learn, debate, argue, and come to a conclusion, which kind of at the end will enable, even richer reasoning and even richer social awareness and adaptation in the different domains and scenarios that we will kind of launch them in. So thought this was a very cool, unique paper in that sense, where it's looking at the social aspect of the agents, which is key and critical, especially as we kind of come into more of a multi-agent system and structure in the future, which I think will become more common as we move forward. All right. And lastly, wanted to just firstly thank you all for being here and listening in. For any other foundations, agents build on a lot of key LLM transformer foundations, attention, fine-tuning, pre-processing, and even further down basics of embeddings, regularization sampling. A lot of these key foundations that are essential before you even kind of jump into agents. We have primers on Vinija.ai. I'd love for you to check it out. Also have a primer on agents itself, covering in depth from the very beginning of how they're built from the foundation to for example, evaluation with abstract syntax tree, which will look at evaluating agents in a very granular sense. So what it will do is it will take the agent and figure out the different outputs it can have for each scenario. With each output, say it's a function call, it will then delve deeper. Did the function call have all of the accurate parameters? Did it have optional parameters? Were they filled? Then it will start looking at each of the parameters types too. When the agent, defined the output parameters for a specific API call, did it use the right type? Was it string? Did it use int? And then it will get even more granular at every single iteration in order to kind of evaluate if your agent is doing your tool calling and your output correctly. All of that detail is already baked in the website, um, and would love for you to check it out. And if you have any questions after this, feel free to ping me on LinkedIn. And thank you so much.